Hi everyone, so this is a review for chapter 14 revision quiz set 1. So based on the responses received here, we'll be discussing question 5, question 8, question 11 and question 17. So let's move on to the first question. Question 5. The graph below shows the variation of pressure P with volume V of an ideal gas undergoing a cyclic process. So when they say they are showing the variation of pressure and volume, what they are actually saying is just a graph below shows a PV. Actually what it says is just a PV graph of an ideal gas, and this ideal gas is undergoing a cyclic process. So cyclic process is the process where the initial state and the final state are the same state. Means by if you look over here, let's say it starts from P, let's say, then it goes up, come down and goes back to the initial state. So it means by the final state after going through the whole process will be equals to the initial state. That's why we say it's cyclic. It goes through a complete cycle back to the initial state. Okay, so the point P, Q and R represents 3 states of gas. So P is one state, Q is another state, R is another state. Okay, so every dot we put on the PV graph represents a state. So to be more specific here, they are interested in this P, Q and R state. So which states of the gas are the coldest and the hottest? Okay, so now they ask for coldest and hottest, so let's do a bit of writing. Probably that will help. Coldest. What does coldest mean? Coldest means that it should have a lowest temperature. Among PQR, you should find the one with lowest temperature. Okay. How are you able to obtain lowest temperature? Well, this is a PV graph, they don't give you T. So what you need to do is to find the relationship between P and V to T. So you know the relationship that PV is equals to nRT. So if it's a sealed container with gas, then the N should be constant, the R is a constant. So if you want this to be the lowest, then your PV will have to be lowest as well, okay, because nR is a constant. So now you know that you need to have the lowest PV. So that's for coldest gas. For the hottest, the whole logic is the opposite. If you want to find the hottest gas, that means you want to find the gas with the highest temperature. So highest temperature, well, it just corresponds to the highest PV. Okay, so for this situation, if you want to find the lowest PV, I think it's quite direct here. You can see that comparing P and Q, P has the smaller pressure. At the same time, if you compare P and R, P has a smaller volume. So immediately you know that P will have the smallest product of P and V. Because the P is the smallest, the P has the smallest pressure among all 3 points. At the same time, P has the smallest volume among all 3 points. So in that case, we can say that P has the smallest P, has the smallest V, smallest pressure, smallest volume, so it will have a lowest PV. So we can, without any very complicated calculation, we'll know that point P will be taking the coldest, will be labeled as the coldest gas. So with that, we can eliminate the others, which is these 2 options. So now we are left with which one is the hottest. Hottest, you have option Q or R. Option Q, you see that you have a higher pressure, but the volume is not as high as R. R has a highest volume, but the pressure is not as high as Q. So it might be difficult for you to determine which one has the highest PV. So what can we do? It's just doing some calculation. So for here, if you're not sure, you can just do calculation. PV for Q is equals to, the P is 4 times 10 to the power of 5. The volume is 1 times 10 to the power of negative 3. So if you calculate that, you get an answer of 4 times 10 to the power of 4 times 10 to the power of 4 times 10 to the power of 2. And it will be Newton meter. Why Newton meter? Because Newton meter negative 2 times meter cube. Then you will get Newton meter. Okay. Then for P for R, PRVR, you can calculate it. The volume is 1 times 10 to the power of 5. V is 5 times 10 to the power of negative 3. So if you multiply these two things together, you get 5 times 10 to the power of 2 Newton meter. So you can see that this will have a larger or higher PV. So in that case, we can select R to be the state, which is hottest. So with that said, we pick our answer to be this one. Okay. So when they ask for temperature and you're unable to get temperature directly, what you should do is try to relate temperature with something that is given here. You are given pressure and volume. So you need to know to relate these two things together, you need PV equals to nRT. Okay, so that's all for question 5. Let's move on to the next question. Question 8. The graph below shows the variation of pressure with volume for a mass of gas. So again, when they say variation of pressure with volume, well, what they are just saying is just it's a PV graph. For a mass of gas, well, if they say it's for a mass of gas, so we can sort of assume that there's no change in mass. Okay, when we say there's no change in mass, what it will mean is the number of moles should be constant. Okay, so what happens to the heat transfer, internal energy, and the work done when the gas changes from state R to state S? Okay, so if you look at the diagram here, R will be here, S will be here. So let's determine what has happened to the pressure, volume, and temperature when this gas undergo a process going from state R to state S. So for the process of going from state R to state S, we see that the pressure increases. We also see that the volume increases. Okay, if you are wondering how I see that so easily, well, you just need to identify this is P initial, then this will be P final. So from P initial to P final, it's an increase in pressure. Whereas for volume, this is initial volume, this is final volume. As you can see, the number gets larger. So it's an increment of volume as well. So P increase, V increase. So if you know that P increase and V increase, you know that if your N is constant, then under the idea of PV equals to nRT, if these two things increase, then your temperature will increase as well. So T increases. So if you don't want to do it mathematically, you can do it graphically as well. You might be familiar with the idea of isotherm, I believe. Okay, you learn it when you're doing isothermal processes, or you are learning about Boyle's law, learn about isotherms. So for this situation, you can see that R will definitely be an isotherm that is lower compared to the S isotherm. So the isotherm for T1 and T2, you definitely know that because T2 is situated higher, the isotherm is higher in the graph, so the temperature should be higher as well. So the temperature actually does increases. So you can look at it graphically, or you can look at it through the formula PV equals to nRT. So knowing all this, how can we relate to heat transfer, internal energy, and work done? Let's do it slowly. Well, when we talk about heat transfer, that will be a bit difficult because heat transfer doesn't necessarily mean P increase, V increase, or T increase. So let's just skip that for a while. Let's go to internal energy. So we know that internal energy, you can represent it with the formula of U equals to F over 2 nRT. So if all this here is constant, R is constant as well. I should be a bit more careful. So F over 2 and R is constant. Then you know that if T increase, then U will be increasing as well. This is based on this. So you know that the internal energy should be increasing. So this means internal energy increase. So the next thing that we want to see is work done. Okay, let's go back to heat transfer at the end. So now let's go to work done. You know that work done is, the actual thing is integrating P over dV, but we don't really need to know that much. We just need to know that when volume increases, then you know that it will be work done by the gas. If it decreases, then it will be work done on the gas. Okay, this is what you learn probably from a lecture note. So for this case, we know that our volume is increasing. So with that, we can make a conclusion that there will be work done by the gas. Okay, if you are wondering why when V increases, work done must be by the gas, you can think of it like this. If this is your gas container, and this is your piston, you can think of it like this. Pressure must be a pushing force. Pressure is a pushing force, it's not a pulling force. So if you want the volume to be increasing, then your piston must move to the right? So I said pressure must be a pushing force. So if you want the piston to move to the right, that means something have to push towards the right? So if you want to push this piston to the right, you can only do it from the inside. You can only do it from the inside to push the piston to the right. You cannot push it from the right hand side of the piston because that will be pulling already. Okay, if you are doing from this side, then you'll be pulling already. But pressure doesn't work this way. Pressure is a pushing force. So if it's a pushing force, you know that it's impossible to do it from the outside. It must have been done from the inside. So if it's done by the inside, means by it's done by the gas inside the container, not from the atmosphere. So it's work done by the gas. Okay, I hope this can help you to understand why it must be by the gas, not on the gas. So you know its internal energy increases, work done is by the gas. You can successfully eliminate what? This one is on gas, you can eliminate. This one is on gas, you can eliminate. So now you are left with whether it's heat transfer released by gas or supplied by gas. To know that, you have to relate internal energy work done, and heat. So you know the formula will be the first law of thermodynamics. So this is the equation that you have, and since we know that internal energy increases, then final minus initial, final is larger than initial, so you know that this will be a positive value because internal energy increases. Then you also know that for work done, it's work done by the gas. So this should be positive as well. So now what should come out here is your heat should be, no, is it? Yes, yeah, I'm fine, yeah. So for heat, it should be positive as well. How do I know it's positive? Let me demonstrate it. Okay, so let's say I plug in numbers now. I'll say delta U is equal to 5. Then I say I don't know what is Q. Then I tell this is negative. Then this is a positive value. Let's say it's 3. Okay, now can you tell me, is it possible for Q to be a negative number? Well, it's impossible for Q to be a negative number because no matter what, you have to bring Q to the other side, and you have to bring the 3 to the other side, then it will be a plus. So know that it will be definitely larger than this value, then this value is positive. That's why if you want to be larger than this value, you have to be positive as well. Okay, you might need to take some time to think about it, but knowing that delta U and W are both positive, then you know that Q should be positive as well. It's just mathematics. Okay, so with that, you can see that the Q is positive means by its heat being supplied to the gas. Okay, if you want to think of it another way, you know that the energy increases, the internal energy in the system increases. It's like you have more money in your wallet after the process. So you know that this process W here will drain energy. Okay, because work done is positive, then you have minus here, means by this process here will take out money from your wallet. So if your changes, if after this process you have more money, but you have this process which takes out money, you need to know that the Q will need to put back more money so that you have more money in your top bag, in your wallet. Okay, so let's say you have 5 ringgit here. You know this process here will take out 3 ringgit. So if you have a process that take out 3 ringgit, but at the end you want to gain 5 ringgit, you must have a process which provide more money into your wallet, right? So you need to have a process which give in money to your wallet. That's why it should be a positive gain of money. That's why the Q should be positive. But there's many ways of thinking about it. This is just a slight analogy. Okay, so at the end we know that it's heat supplied to the gas, so the answer should be this one. Sorry, it should be this one. Supplied to gas, internal energy increases, work done by the gas. So that's all for question 8. Let's move on to the next question. Question 11 says, a sample of ideal gas undergoes 2 separate processes, an adiabatic compression and then isothermal compression. So now they ask which of the following correctly describes the heat flow for each process. So they are asking about heat flow, means by our focus will be on Q, because Q is just heat flow. So let's write down the 2 processes that we have. We have adiabatic compression and we have isothermal compression. So we have to be very clear what are these processes. in order for us to know how does the heat work here. So adiabatic compression, the idea of adiabatic already tells you that the heat flow should be 0. So this should be very straightforward. You can straightaway know that the answer will be for this and this is correct, for this and this it should be wrong. Because adiabatic itself means no heat flow. So the heat flow should be equal to 0. Very direct. So the next thing, which is isothermal compression. For isothermal compression, you know that the temperature should be constant. And you know that because it's a compression, then you know that the volume should be decreases. So if volume decreases, that will mean it's work done on the gas. Again, if you want to draw a piston, volume decrease means by the piston must be moving to the left. So we know that pressure is a pushing force. So if you want to push the piston to the left, you can only do it from the right hand side of the piston. You can only push from this side. You cannot push from this side. If you push from this side, the piston will go to the right. So you have to push from this side, means by it's the environment pushing the piston. So environment is the one pushing, so the gas is the one that received the push. That's why it's work done on the gas. The gas received the work done because it's pushed by the surrounding. Okay, so it's work done on the gas, so you know that your work done is negative. That's just sign convention. Work done is negative. Then let's go back to isothermal. T constant, will be saying that U is constant. Why when T constant, U is constant? It's because U is equals to F over 2 and RT. So usually there's nothing that changed for here. So if your T is constant, then your U will be constant as well. So knowing that, we can further deduce that delta U will be equals to 0. Okay, that's a lot of info. Let's combine the delta U and the W with the first law of thermodynamics. Delta U equals to Q minus W. You know, delta U will be 0. W will be a negative value. Okay, let's shift it into a way that we can understand easily. So after shuffling this thing, we know that if W is negative, our Q should be negative as well. So Q is negative. What does it mean? Okay, let me move this out a little bit. Q is negative means by the heat is flowing out. Okay, so with that, we can say that the answer is C. Okay, so that's it for question 11. Let's move on to the next question. Question 17. It says we have two equal masses of an ideal gas initially at STP. So two equal masses means by the N for one gas should be equal to the another gas. So it's an ideal gas, it's the same ideal gas, just that you have two systems probably, then both of the system have equal masses. Okay, if you want me to draw it, it will probably be something like this. You have a box here, then you have another box as well. Okay, so for these two boxes, you have N1 and you have N2. but we know that N1 is equals to N2 and they have the same number of mole, and they should have the same it's the same ideal gas, so we can make proposition that molar mass 1 is equals to molar mass 2, then is equals to the same molar mass. And they are now being compressed to 1/3 of their initial volume. So means by after being compressed, they should be left with this much of volume. It is a rough drawing. But we know that they have the same initial volume. Oh, now here's the issue. Okay, I should remove this. I cannot do it in 1 and 2 because that would mean by initial and final. It's a bad thing to do. We should change it to A and B, system A and B instead. So that's what and A and AB and A and MB. So the number of mole of system A is equal to the number of mole of system B, and they both have the same number of mole. The molar mass of system A is equal to the molar mass of system B, and we can call them M. Then they're initially at STP. So initially means by T1A here, TA1, TA initial is equals to 273.15 Kelvin, and it's the same for system B, and it's equals to 273.15 K. Why do I know it's 273.15 K? Because it's standard temperature and pressure. So the standard temperature is 0 degrees Celsius, the standard pressure is 1 atm. So pressure of system A initial is 1 atm. Pressure of system B initial is 1 atm as well. And after being compressed, they are having the same final volume. So I can say VA1, this is VA2, then VB1, sorry. Oh, there's too many subscripts here. This is VB1, and we can say they start out the same. So VA1 equals to VB1 equals to V1. And they are being compressed to 1/3 of their initial volumes, means by VA2 is equals to 1/3 VA1, whereas VB2 is equals to 1/3 VB1. And since they compress by the same amount, we can say that the final volume should be the same as well. So VA2 equals to VB2 equals to V2. So this is what we know. So now the last thing, one of them is compressed isothermally, while the other is compressed while it's being thermally isolated. Thermally isolated means by there's no exchange of heat. No exchange of heat. So we say when there's no heat exchange, what it will mean is there's no heat flow. And no heat flow, we can know that it's actually an adiabatic process. It's an adiabatic compression, to be specific. So we can know that system A, it's an isothermal compression, whereas for B, it's an adiabatic compression. Now they are asking for which are the same for the both sample of gases. So what are the same? We have to look through all of them to determine what is the same, what is different. So first thing is the temperature of the gas. Well, they start out with the same initial temperature, but as you can see here, because system A is undergoing an isothermal compression, you know that the final temperature of system A will be equal to the initial temperature of system A. So the temperature will not change for isothermal compression. But for system B, because it's not an isothermal compression, it's an adiabatic compression. If you look at it, delta U is equals to Q minus W, but because Q is equal to 0, that's why delta U equals to negative W. So now we know that this is a compression, then the work done should be on the gas, so it's a negative. So here you get a positive delta U. So your internal energy would increase. So if your internal energy increase, what it will mean is your temperature should be increased. So the temperature is not kept constant for system B, whereas for system A, it's kept constant. So if one is changing, one is not changing, at the end, the two samples of gases should not have the same temperature. That's why A is wrong. Let's look at internal energy of the gas. Well, temperature is directly proportional to internal energy. So if the temperature is not changing for isothermal compression, then the internal energy should not be changing as well. Whereas for system B, adiabatic compression, because the temperature is increasing, therefore the internal energy should be increasing as well. So one internal energy is not changing, the other internal energy is increasing. So if that's it, we know that the internal energy at the end should not be the same for both samples of gases. So we say this is wrong as well. Next thing is work done on the gas. So to find the work done on the gas for isothermal compression, you need to do an RT logarithmic natural log V2 over V1. Whereas for this adiabatic compression, the work done is beyond your syllabus. So with that said, if it's beyond the syllabus, means that it's definitely not something you learn in your syllabus. So know that the formula to calculate work done should not be the same. So if the work done calculation should not be the same, you can briefly assume that the work done calculated should be different as well. So since they are different, then this will not be our answer. So our answer should be the density of the gas. Well, it's actually very straightforward that density of the gas should be the answer because your N is constant here. The number of mole is constant here means by the mass, the total mass of gas inside the container should be kept constant throughout the process. The mass is kept constant, the final volume are the same. So if mass is the same for both systems, the volume is the same for both systems, you know that density is just mass times volume. So number of mole times molar mass divide by the volume final. This should be A, then this should be B. Number of mole for B, molar mass of B, then you get mass of the system B, then you divide by VB2. So VA2 is equals to VB2, NA is equals to MB, MA is equals to MB, so you know that rho A is equals to rho B as well. So the density should be the same because they have the same volume, they have the same mass of gas inside the container. So the density should be the same. Therefore, the answer should be this one, density of the gas. So that's all for question 17, and that wraps up our review for chapter 14 revision quiz set 1. Thank you very much.